Welcome everybody to the third lecture in the fall series, 2010. This is the third in a series of life cycle efficiency in buildings. Today, well first let me just, restrooms downstairs and upstairs if you need them, exits in the back and on the side. And I want to thank our sponsors, Idaho Power, Northwestern Energy, and Better Bricks. We have two gentlemen with us tonight, luckily, very luckily in Ian's case, because he had to come through the storm of the century or the weather bomb, I guess that's what they were calling it, to get here, delayed in Chicago. And Benjamin, they're both at the National Research Council Canada in the Indoor Environments Group. We will be answering questions online for those of you out there. Please email idl@uidaho.edu, and I'll get your answers, or I'll get your questions answered online. Tonight, we're going to be talking about, Ian will be talking about simulation beyond code compliance, looking at how to use simulation in the design process. Benjamin's going to be talking about the role of wireless sensor networks for energy prediction and reduction. Benjamin hails from Australia, Ian from Scotland. I couldn't remember all of it, so I'll maybe let you guys do a little bit of that yourselves. And again, but both work now in Canada for NRC. So with that, I'd like to give to Ian. Actually, yeah, I'll just put this up here. And you have yours.
Okay, so you're going to have two very different accents tonight in the presentation. So hopefully you can follow along what we're saying. Okay, so just a quick outline of my presentation. I'll have a quick introduction. I'm going to talk a bit about integrated simulation and then the need for performance assessment, and what this can do in terms of decision support. And I'm really going to focus on a few case studies. There's about half a dozen case studies that I'm going to focus on to show you more what simulation can do and help you with in the design and operation of buildings, rather than talking about nitty-gritty details of simulation tools. Although I have the odd slide that's got some detail in it. None of the work that I'm presenting would be possible without former colleagues of mine at the Energy Systems Research Unit at Strathclyde University in Scotland. I worked there for over 10 years before coming to Canada, so a lot of the work that I am presenting tonight comes from that experience back in Scotland. And I've also plundered Google and two architecture websites for some photos and images. It's fairly obvious the ones in Glasgow from the Glasgow Architecture and the ones in Edinburgh from edinburgharchitecture.co.uk. Just a little bit about the background in Glasgow, where we had an energy design advice service where designers, building architects and engineers were put in contact with simulation specialists. And that was like a consultancy type service. And then I was leading the Scottish Energy Systems Group before I left for Canada. And the idea there was that the specialist would be embedded in the company with the practitioners, so that rather than having this kind of like conversation between a client and a consultant, they would be physically in the same place, and you'd get much more rapid decision support, and also show the engineers how simulation tools were used in practice, not just the results of the simulation tools. And a lot of the work that the examples I'm going to show you come from work we did on both with clients from both of these schemes. Very quick review of simulation. Simulation isn't new, basically, is the point of this slide. Like 50 years ago, back in the 60s, Gint Metalis worked out how to do the response factor method and invented building thermal simulation. That method's still used in DO2, so eQuest uses DO2, for instance. Since then, there's been a huge amount of work done, and people got really excited in the 80s with all the possibilities with computers and linking things in together. and then attention focused on how to make the tools useful in the 1990s. And then come this century, we've kind of got all this power of these tools, and all we do is use it generally for code compliance. This slide here was from the English and Welsh building regulations, how to use simulation to prove that your new building here or a refurbishment project, and you'd follow through through all this, and you'd hopefully get to the point where you'd achieved compliance and you'd tick the box, you'd done your simulation work, everything's happy, right, we can go home and have a beer or whatever. So the two things, or one thing to really, two things to draw from this is, like, you've got these tools, they're going through this like hugely complicated process just to do one thing, and that's code compliance. It's a valid thing to do, but you're just skimming the surface. The other thing as well, in terms of real building performance, and it's kind of touched on here, is that for a lot of compliance checking and code work, activity schedules and various aspects of the building are predefined, and they may have very little resemblance to the real activity schedule or real use of the building. And there's good reasons for that, but it means that in a lot of cases, the predicted performance from a code compliance type run is not similar to the real building performance. So you've got these wonderful tools, they can do a whole load of things, and what else could they be doing? One thing they can do is predict as-built performance. If you put the correct data in, then you're going to get good answers out. All through their use, if you use them correctly and wisely, you can make good decisions and informed decision making, rather than saying, well, I think that's going to be slightly better than that. You're actually quantifying changes in performance. All of this work requires an integrated approach. And part of the reason for that is that buildings are just inherently complex. We like to think of buildings as relatively simple in a lot of cases, and I don't think enough credit is given for just the complexity of all the different interactions going on in the buildings. And if we have, say, for example, this person here is in the building, they're breathing, so they're giving off carbon dioxide that needs to be ventilated out of the building. They require fresh air. They're also a source of moisture for the building that needs to be dealt with somehow. They're also a source of heat, which will contribute to overheating potentially in summer within the building. Their actions, if they switch, say this, if I can get the mouse back, the kettle on or the lights on, are going to increase moisture loads and heat loads within the buildings. And then all of these interact with the fabric of the building. And there's all these interactions going on even before we get to modeling like the HVAC system. So we've got these incredibly complex interactions within the building, and a lot of the time we'll go in, we'll say, yeah, the building's like relatively straightforward, it's just a quick bit of architecture. We've got our structure in place, and we'll focus all our attention on HVAC. Whereas it's the building itself that's driving what loads the HVAC is going to have to meet, and there's a huge amount of complexity going on there. As you simulate a building, all the knowledge that you're gaining about how it's performing and all the interactions and how one action influences another part of the performance, all this knowledge can be used to help improve the design of a building. Going back to what I said a couple of minutes ago, engineers did this, and engineers and physicists love to break problems down into manageable chunks that we can deal with. So the buildings were traditionally broken down into building systems and HVAC systems, and in the HVAC we're going to concentrate just on the thermal performance of our HVAC. Oh, but wait a minute, we also use electrical power in our HVAC, so we better have some model for all those electrical flows, and so on and so forth. And all of these individual technical domains have to talk to each other somehow, and these are modern simulation tools deal with this complexity. But what was forgotten in all that rush to get the technical complexity of the systems is, what about the people in the buildings? What do the people want? What is the influence of people in buildings? What effect do they have on buildings? What effect does the building have on people? And that is one of the key areas of research that a lot of that we are certainly involved in just now. There's just a quick list of tools. There's different levels of tools. There's the integrated tools. There's single issue tools which try and just look at individual aspects of performance. And then there's a whole host of simplified tools which give you, underneath them there's complex simulation engines, but the interface has been created in such a way that you can get to useful information with less pain than if you were using the detailed tool itself. I have to say, having been trained in Energy Plus ESPR and IES, they're all equally hard to use. They've all got their advantages and disadvantages, and some have strength in one area, and it's easier to define some aspects of the model, and others, it's vice versa. Whichever tool you're using, though, what you really need to do is assess what you want to get out of the analysis you're doing. So going back to the code compliance, if you want to see if your building is code compliant, you run through the process, be it the Title 24, be it ASHRAE 90.1. You run through that, you know what you're doing, code compliance, that's our performance assessment we wanted to look at. If you want to look at local thermal comfort and discomfort, then you might want to start looking at, say, a CFD. You might want to look at visual discomfort here. You may want to look at daylight assessment, so daylight factor calculation. You may want to look at would mold grow in the building surfaces. So here we can see these black patches are actually mold in a real building. And this curve here is the growth limit for this type of mold here. So we're seeing that that mold could grow in this building. You may want to look at the environmental impact of the embodied energy within the materials you're using on your building. All of these are potential performance assessments that you can do with an integrated tool or a single issue tool. You just need to define what performance you want to assess. And then here's VOC emissions, so volatile organic compounds coming off of the construction materials. How do they diminish over time as you ventilate the building? Acoustical performance. And you can also integrate all these performance issues into one view, and to try and say, if you generate a few of these for one building, then you can see the trade-off between, well, I've made the daylighting better in the building, but my cooling loads have gone up, and start to trade off one performance aspect against another, and use the design and design skills to say, well, yes, that's going to be so much more of the cooling load, but it's going to be a nicer looking building and people are going to be happier in there because the windows are bigger, whatever. So you can inform your decision making that way. And there's huge amounts of detail within these tools. Just to draw this part to a close, it's important to know not only what you want to simulate, but also what physical processes you're trying to capture in there, and know what your suite of tools can do. The design practices that I was involved in generally had a range of tools that they would use. They had some very simple tools, they also had more complex tools. And depending on the budget for the job and what was required of the performance assessment, they would then select the tool that was appropriate for that design question. The process of abstraction, if you've never heard that before, is where you take the complexity within a real building and simplify that down to the essence that's required for the model. So do you need to model every aspect of a design? Do you need to model these windows as separate windows, or could you just model that as a single glazed area, say here, or with the equivalent area? And that's the kind of abstraction questions that you can ask yourself, and it simplifies the model if you can, and then you can get to the performance information much faster. So what kind of performance information can you get out of these tools? This comes from, I believe it's ArchiCAD, and this was linked in with a constructions database. So the architects in this practice were doing fairly simple block models, in 3D and then attributing those surfaces with construction materials, at which point they have information on surface areas and volumes within the building, but also which materials were used in that building, so they can start estimating costs, environmental impact of those materials, so on and so forth. You can also, with fairly simple block models, start to look at solar access issues, or in this case, export it into a CFD software. And what we're seeing here is the prevailing wind on this. This was a large hospital here, and the prevailing wind was on this side of the building, and the red arrows here are areas of high pressure. And this was at the bid stage for this job. The architect wanted to have an idea of how much of this facade required special treatment in terms of the pressure and the wind-driven rain on that facade. So they were trying to quantify that really early on in their, before they even had the job. And they were just running a relatively simple CFD simulation to quantify how much of that facade required special treatment, so they could get their bid a little bit better tuned for the job. Another example just with shading here, looking at the impact of existing buildings, say on this building in the middle, and the impact of this building on the other buildings within this area here. Very simple models, very quick and easy to make, but starts to give a message. A little bit more effort, and you can look at, say, something like this, which is an art gallery in Edinburgh, and looking at the direct sun coming in on the rear wall here and falling on that painting there, which would not be good for the artwork. Obviously, if your design question is, how will this thing actually look, then you need to go to much more detail. This is a model from the Radiance website, I think, so using the Radiance simulation software to calculate obviously very detailed reflections and water effects and things like this of the entrance to the Louvre in Paris. When you've defined what you want to look at and how you're going to model it, you also need to look at what conditions are we going to analyze its performance in. So on the daylighting side, daylight factors, the standard measure of daylighting within a building, daylight factors are defined for an overcast sky, but we know that the sky is not always overcast. So you possibly want to look at your model with the overcast sky, but maybe some other sky types. And if it's a clear sky with the sun in it, what time of year do you look at? Do you look at the winter solstice, summer solstice, spring? When do you look at that model? Likewise, if you're doing a thermal analysis or an airflow analysis, then what conditions are you going to look at? Are you going to look at your peak wind flow conditions? Are you going to look at a CAM condition? Are you going to look at something in between, your average condition for the year? So there's lots of decisions need to be made when creating your model. So moving on to the example projects, I think I actually have half a dozen, but this is just a quick summary of different projects here. And some of these are retrofit projects, some of them were new build, some of them were integration of new build into existing buildings. So there's a large variety of projects. And the idea here is to show kind of the power of simulation and what it can be used for. This first building here, this is in the centre of Glasgow. So this was the historic warehouse district of Glasgow. And this is the completed building. So the project we were involved in was helping to convince the city planners that this building would not have a negative impact on the buildings that are just out of this photograph on the opposite side of the street in terms of solar access and daylight factors within the buildings that were opposite it. Google Street Map view here of, you can see the downtown grid pattern in Glasgow. This was the building here. Interestingly enough, the subject building for this analysis was on that site, and a couple of months after this job was completed, it collapsed. it was about 300 years old and had trees growing out of it. So it was a kind of pointless exercise at the end of the day. But we can see here, so this was the Gap site, and it was just a vacant, empty downtown core site. This was the historic building with the trees growing out of it. And then here we can see just the outline of the new building there. So again, very simple models, just block models of the existing buildings, a little bit more detail in this one just to give a little bit more idea of the scale of the image or the scale of the building. And here we can see the shadow pattern coming across this building. One of the issues here that we debated was, should this site be modelled as an empty site? Because traditionally there was a building on that site. There hadn't been for 50, 60 years, but in reality there should be a building there. So should the base case be an empty site or a site with a nominal building on that site? We went with the empty site and compared the two, and this information plus the calculations from daylight factors in a couple of these rooms was enough to convince people that the building would not have a negative impact on this old warehouse property that, as I say, subsequently collapsed.
Is that near the Charles Rennie McIntosh's school?
About a mile away.
Wow.
Yeah. So it's southeast of there, down nearer the river. This is a quick residential one. It was we did a couple of solar access models like this. This was just really interesting because of the modelling of the trees. And the question here was, there was a property on a wooded lot, and they wanted to remove some of the mature trees to maximise their solar gain to the building so that they could have reduce their heating demands. Google Maps isn't quite detailed enough to show us the house, but that's the images of the trees that were supplied by the architect, and the question was how to model those trees, and this was the resulting model here, and we can see. So this is the house here. It actually had a pitched roof on it, but there was no need to model the roof because that wasn't having an impact on the lighting within the house. And these are the trees. We decided to model them in full leaf and not try and guess at some sort of transparency of the leaves and the trees. And I believe this was the final model with the trees removed from it. Here we can see the daylight factor results. So there's a window here. The initial model with all the trees, daylight factor of 14% and 7%. Remove the trees and that daylight factor goes up to 27% and 16%. Daylight factor of 2.5 at the back of this room, which is more than adequate for daylighting. The rule of thumb, before it was down at 0.5%, so it's going to be quite dark at the back of that room. Moving across to Edinburgh, and this what is currently the High Courts in Edinburgh used to be the Parliament buildings back in the 1700s, or the 1600s and 1700s. So these are incredibly old buildings. They're built up near the castle, if you know Edinburgh at all, and the hillside there slopes off at quite an angle. And this here is ground level. We've got 3-4 stories above here. If you go in at this ground level, there's also, I think, 7 stories going down to the back door of these buildings. So there are lots of complexity associated with being in the middle of a World Heritage Site. Very little that can be done to the outside of the building. And there was lots of different aspects of how to improve the performance of these buildings. So they had been refurbished, the HVAC system had been refurbished in the 60s, and that was just a disaster. So they were trying to take that old HVAC system out and try and use some natural ventilation within the building, which was what the original design had in place, and looking at how they could use daylight and improve the thermal comfort of occupants. One of the big issues was the design occupancy of the courts was pretty much like our room is just now, fully occupied. But in reality, most of the time, there was maybe only half a dozen people in there, because most of the court cases, or a lot of the court cases that go through there, there's no need for a jury. So there's a judge and a couple of lawyers and the accused, I guess, and there maybe a couple of other people. Here's the Google image of the site here. For those that know Edinburgh, the castle is just up here. So a very tight site here. This is where it slopes off downhill considerably. This is a bridge running quite a few feet above this road down here. And there was some infill courts and new build going in here. There was solar access studies that we looked at and thermal performance. And here is one of the models. Again, very simple model. And there's one thing I want you to take away tonight is just keep the model simple when you're doing this, so you can get the most amount of information out that you can. We can see in this rendering where the daylight is coming in there. There was also daylight. There was daylight coming from both ends of the courtroom. So we had a fairly even daylight factor here between kind of 1% and 2% throughout the room. And one of the issues that was looked at was this area up here is exposed thermal mass, and then this was wood panelling in the lower area. And there was different heights of wood panelling, and trying to get that trade-off between the amount of exposed thermal mass and the performance benefit that gave in terms of the night cooling scheme and the thermal comfort of the occupants within that courtroom. There are some graphs of the temperature profile within the space. One thing to pick out from this is just looking at this performance. It's just a 3-day simulation, and so really looking at short time periods, so we can just really focus our analysis down. Looking at the night ventilation scheme, this is only a 2-day simulation, but the thing what we've selected here is a period where we've got cool overnight temperature, then it gets warm during the day, and then we've got an overnight where it stays relatively mild, and then mild during the day. So we've got two very different boundary conditions, weather days here, but our performance is still reasonably good in both cases there in terms of resultant temperature in the court. It stays within the control parameters that we're looking at there. The other thing here is we're simulating at very short time steps, a 2-minute time step, and you can see all this oscillation here as the natural ventilation dampers were controlled with an on-off control. So they were busy opening, closing, opening, and closing, opening, and closing. So there was a control issue here. And as we were developing this model, questions were going back to the engineers, how exactly are you going to control this? And they were saying, we just want to know the size of these openings. We don't want to think about the control just now. So there's got to be that interaction between where you're creating the simulation models and the details that you need there, and also what's appropriate at the design stage. This again, the other end of the Royal Mile in Edinburgh, the new Parliament building. And this is a photograph of the debating chamber here, taken during construction. And you can see the seats where the members of Parliament would sit in an arc round here. Of interest here really was the thermal loads in here were quite extreme because of large solar gain through this wall, which had these semi-transparent areas. This was a thin wooden veneer between two sheets of glass, and it allowed some light through. And then there was larger areas above that with just normal glass in it, so transparent glass, and then all the lights for the TV cameras within there. So there's a lot of thermal gains in there, and various design questions that came up. Here's the Google image of the site. So this is the debating chamber that you were just seeing the picture of. These are other buildings on that site, the complex. This was the historical building that had to be accommodated and, interestingly enough, made bomb-proof, which that was a challenge for a 300-year-old building. And one of the initial issues that we were asked to look at was there was a lot of shading devices being added onto the side of the debating chamber here. And you can see some of the fins here that they actually carried on through the design. And what they weren't thinking of when they were looking at just this part of the building, the design team was split up looking at individual parts of this project because it was just so huge and complex. So the part of the design team that was looking at this part forgot that there was all these neighbouring buildings round about. So they were really worried about the afternoon solar gain to this space and the sunshine coming in. And as you can see here with this rough outline of those kind of elliptical shaped buildings, in the afternoon these buildings perfectly shade this wall of the debating chamber. So there's not really any need for shading on this debating chamber. And because they weren't considering this neighbouring building, they were investing a lot of time on the shading unnecessarily. So again, this is clearly a more complicated model of the debating chamber, but a very simple shading model here to show the impact of that shading on the debating chamber and thus informing that part of the design decision. This is the rendering of the inside of the building and of the debating chamber, and you can see here the various aspects of the model. What was interesting with this is this model, the architects were working in 3D, which was relatively novel at the time. So they were putting this model together in 3D in the CAD software, and it was possible to transfer this all the way through to the daylighting design tool via 2 translations. We did this, and 2 interesting things came out of this. One was that there was various walls that weren't actually modelled in the CAD package, because the CAD package was just modelling everything as lines and surfaces, and when you looked at it in the CAD, everything looked complete, but because nothing was actually rendered in the CAD model, then those parts were missing from the model. So the initial analysis of here showed that there was daylight factors of 50% or something in here because half the models were missing. The other interesting thing was just some of the detail that was lost in the model as it went through this translation process. And this is one of the things that people have been struggling with in the interoperability of tools, and things like BIM are trying to address that just now, so that you can much more easily take all that effort that's been put to design a model in one piece of software and get it into another tool relatively easily. These circles here were focus points for the artificial and daylighting analysis that was done, and that was undertaken in 2 stages. The first stage, we looked at the distribution of daylight within this space, and we showed that it was nice and evenly distributed, the daylight. The area to the back around here, there was some high level glazing as well as very high level glazing up here, and the light would reflect down through the space. So it was a nice even daylighting within there. The question was raised by the TV consultants, lighting consultants. They got worried that the artificial lighting and the daylighting would interact, and there would be lots of funny effects on the way people would be lit up for the TV camera. So you'd have different color temperatures from your daylight and your artificial light, and an orange shadow and a blue shadow, say, if you had it not evenly distributed. So they didn't like any of this daylighting within the space. So we were asked to then model the artificial lighting in here. So the next question is, okay, so what type of lights do you have? How many do you have? Where are they? What direction do they point in? And all this. So none of these questions could be answered by the design team. And eventually the model came down to one of these spheres next to a window with an artificial light shining the other way. And that was the model that answered that design question, just a very simple model and none of this complexity. And I'll admit that we spent quite a while with the artificial lights, putting them into this and trying to get them all oriented the right way and everything set up and all this. And in the end, it was maybe a 30-minute model that answered the design question after spending maybe 2 weeks' work on that. So this is one of the few buildings that Charles Rennie Mackintosh designed, and it was used by the Glasgow Herald newspaper as their headquarters for years. And this is it's a sandstone building here. You can see part of it in this drawing here. And the idea was to be refurbished and made into a centre for architecture and the arts, obviously with a considerable amount of new build on the side here. And we were asked, the Strathclyde University were asked to look at if we could make this into some sort of renewable energy, zero energy example building. And this was back in the mid-90s, mid to late 90s, we were looking at this. The focus area, we looked at the building and there was just, we persuaded them only to look at this small area up here, this viewing gallery high up in the building, excuse me, and just to focus on that area because this was at the time where nobody was doing kind of zero energy buildings, and we were just like, let's try and narrow our aspirations down a little bit. But there's this huge complexity between all the different interactions between how this building's going to perform and how the renewable systems are going to perform, how all the passive systems are going to perform, and how do we communicate all that information. So again, this is downtown Glasgow. This is the main railway station with a Victorian railway station. This is where the building is. That's the existing part of the building, and this was the new build around here. This alleyway is only 6 to 8 feet wide across here. So, and this road here goes down to 1 lane for cars. So, and it's 2 lanes here. So very, very tight urban site here, which is why there's no good photos of the building. This is really where this integrated performance view came in, because we wanted to look at various aspects of the building and display it all in one sheet. So we've got our picture of the building, we've got some information about which case this is. So this is our base case model, this is our initial model. So it's our viewing gallery base case model, a little summary there. And we've got our maximum capacity for heating and lighting loads, no cooling and no domestic hot water, other aspects of performance in there. So relatively simple model. We can see what our thermal comfort is. It's not so good in winter. It's getting pretty warm in there in summer. Glare sources, looking out these floor to ceiling windows, there's no glare sources because it's so well lit that there's not a contrast issue. Looking at daylight factors, there's 2 images here. So the red curve relates to the red dots across this floor plan of this area here. Very well daylit, so there's not a problem with the amount of daylight that's coming in there. In terms of emissions for a year's worth of energy use here, and it'd be natural gas on the heating and electricity for the lighting, this is what it would turn into in terms of carbon dioxide emissions, nitrous oxides and sulfur dioxide emissions based on the electricity generating capacity in Scotland. So there's coal getting burnt and there's nuclear power stations and hydro stations. Looking at the profile for energy use at different times of the year, we've got a winter day here, we've got a day from spring and a day from summer. So we can see, just going back through here, there's no lighting control, so the lights are on all day, every day. So we've got this lighting gain every day. We've got heating in the morning in spring, and then the temperature gets a little bit warmer in spring, so the heating goes off. In winter, we've got large heating load in the morning, and then there's residual heating required later in the day. So we started looking at different cases. So this is again exactly the same data as you just saw in the previous one. 220 kilowatt hours per metre squared per annum was our initial energy consumption for this building. So we said, well, you've got all this glazing, your heat is pouring out through this glazing, you don't need that much daylight within there, so you can go to, and I think we ended up with some triple glazed, double OE, argon-filled glazing here with less transmission on it. And what effect does this have on the loads? And you can see here in the spring and autumn season, the load has come down significantly, and in winter we've only got this peak in the morning now, and we've reduced our annual energy consumption. And we've quantified the effect of putting on that advanced glazing. We also looked at using transparent insulation material and lighting control, what would happen there. And you can see the lighting load is reduced now in summer. In spring and fall, there's a peak as the sun set. Glasgow's further north than Edmonton, so it's pretty far north. And then in winter, we've got the lights on, obviously in the morning and in the evening, and our heating load is still up there. Our annual energy consumption's fallen again. Then the heating system was it was a hydronic heating system in the floor they were proposing initially. We then said, well, if you actually had a convective electrical resistive heater that responds to that demand in that space and only at that time, so a much faster response rather than the slow response of the hydronic system just for that area, then you can significantly reduce your peak load and overall reduce your energy demands further.
What is transparent insulation material?
It is basically drinking straws on their side. Is the best way to visualize it.
It looks like that.
Yeah, there's several products out there. The University of Strathclyde had one of the largest installations of that back in the early 90s, and I think it was about 3 or 4 inches thick of white drinking straws on their sides, and then 6 inches of concrete behind that. And the idea is the sun shines, there's a glazed facade here, so the sun comes through the glazing into the straws, bounces along the straws, and then hits that concrete wall, and it absorbs the heat from the solar radiation.
It's like a trauma.
No, it's not open at the top or bottom. So, and that heat is then in the wall, it's then conducted through the wall, like a tron wall, and into the room. The drinking straws, for lack of a better description, they then stop the convective loss off that concrete facade, so they reduce the heat loss off that wall, so which you would have in a tron wall, and in a tron wall you'd also have the air coming up past on the outside. So it's similar but different. In the end, they didn't install TIM or the high performance glazing. What they did do, and we looked at this with renewables, was looking at a wind turbine that was suitable for an urban environment, and we can see the electricity generated during the windy winter and spring period. And then photovoltaic panels, the electricity coming off those panels is the green here. It's also possible for photovoltaic panels to collect heat off them as well. One of the interesting side effects of a PV panel is as the sun shines on it, it generates electricity. It also gets pretty hot, and its efficiency at generating electricity drops as it gets hotter. So it's beneficial to draw some of that heat off the PV panel, and if you can use it in your building, then all the better. So what you can see here is that in terms of the renewable energy sources, there's more than enough energy in the year to match that demand. The problem is that most of that's getting generated in summer and spring when there is no demand. So you've got this complete temporal mismatch between your renewable energy sources and your demands in the building. And that's one of the big challenges of integrating renewable energies into buildings.
What was DWT?
Ducted wind turbine, and that's this fellow here. So this was the wind turbine that's suitable for an urban environment. We've got where I'm tracing with the mouse just now would be the typical building parapet here, and As the wind is blowing against this face here, you have an area of high pressure, and then as the wind goes over here, you will always have an area of low pressure here. It's a common failure point in, say, hurricanes and things like that in Florida and on the corners of buildings and at the parapet, because the forces are so strong. So what we had a guy doing his, where's the mouse gone, his PhD, and he was looking at this, trying to use this pressure difference by basically putting a hole through the building and a wind turbine blade in there to generate electricity. And in this case, it was enhanced by putting a spoiler basically in here with a PV panel on there to reduce the pressure here even further. So that's the photograph or an image of the top there. You can see here, there's the ducted wind turbine looking into them. There's the photovoltaic panel on top of it, and you can see there's some facing east and some facing south there.
How was this building accepted in a town that's such a Rennie McIntosh, rah-rah town?
The biggest issue with doing the whole building, it was really well received, the design of the building and the integration of the new build with the existing. I think the rear facade of this building was just brick or something, so it wasn't that important. And I think Charles Rennie McIntosh did the sandstone stuff, and he really just worked on the facade and the facade only on this building. The biggest issue with these wind turbines that we had was that we built these at the university, and the contractor wanted us to guarantee that they would never fall off the roof. It's like we were saying, but you're attaching them to the roof. We're not going to guarantee your work. So there was a big argument about that.
So do you buy the turbine with the ducts and the spoiler?
These were custom built at the university. As I say, there was a guy doing his PhD on this, and he looked at all sorts of different shapes and designs for this hole to be. And I think the final design was just a straight channel was the best in terms of for all angles of wind coming in.
And did they work?
They turned. I have absolutely no idea how much power they ever generated. I can tell you one thing, even the PV panels, I was wiring those up on an overcast day, and I don't know, when I was doing it, I didn't even think that they would actually be generating electricity at that point. So you got these wires, and all of a sudden you're starting to connect them. There's sparks jumping from them because everything's live, even on an overcast day.
And how do you actually collect the heat from the PV panels?
They didn't integrate that part, so obviously you can't do it here. We had on this south-facing wall, just below here, there was a vertical array of PV panels. And the idea there was just behind, so at the bottom there was an air intake, and then the air would come up and then be taken in to the building. So it was like a preheat behind.
You take the hot air off at the top.
Yeah, so from behind them. And we were involved in a large European project on that. And it basically, you have to have a massive thermal demand in your building for it to make any sense. So it was like leisure centres with swimming pools were about the only place that it made any sense to do that. So future trends, where are we going? Really, simulation engines are going to get improved. They're not, all the answers haven't been, all the developments haven't been made yet. The interoperability and the BIM stuff, I think, is really going to take off in the next few years, and I think that's where a lot of the barriers between the design and the operation of buildings and the commissioning are really going to start falling away. And because we can design good buildings just now, some people can build good buildings, but then checking that performance and getting the building tuned and operating properly is definitely a big issue just now. The main focus on modelling there are areas that are just not that well modelled just now. Moisture transfer within buildings is a huge area, and the impact of that moisture movement is really unknown, and effects of things like that moisture moving into, say, engineered wood products and the effect that has on those. And colleagues of mine are working on that just now. The other aspect is the human factors, so what do people really want and what do they really do in buildings? So trying to get that captured in the simulation models and the behavioural models of people. And then I can see a bunch of new tools coming out. There's one that we've authored, SPM Soft, which is looking at acoustical testing of real buildings. And that really helps in showing that the building is performing correctly or not, and putting and quantifying that. And then all these existing tools can be used to help tune buildings and control buildings and learn more about why buildings are performing or not. So there's areas there. So that very quickly is my summary slide. I am not even going to say what's on it, but yes, there is still more research to be done, and with all these things, as you're simulating a building, it can take the design in a new direction as you start to learn about how the building will perform through that. So I am going to hand over to Benjamin.
And just a reminder, a few more step in, there's a signage sheet going around, and remember it is important to get the location information on that signage sheet. And then maybe questions at the end, and we can get back to you at the end.
We're going to have a general discussion at the end for questions.
Unlike Ian, I might stand. So my presentation's broken down into a couple of parts. The first part, we're looking at a project that we're conducting at the National Research Council, and it's a large project looking at sensors in buildings, basically commercial buildings, and detecting not new chemicals, but designing and building new sensors for things like formaldehyde and radon that are cheaper and have a quicker response time. And we're also looking at other things within the project, so energy predicting tools and generally using wireless sensors in a commercial building. And then finally, if time permits, I'll quickly look at some smart meter data analysis that we have undertaken in our group. So what this project looked at was using basic wireless sensors within the building fabric. So if you've got an old building and you want to get a measure of building occupancy, instead of putting in turnstiles at the front door or getting people to swipe, what other measures or how can we measure building occupancy? So is there places where a lot of people go or use that we can easily measure? The more it's used, we can infer there's more people within the building. And why do we want to know this information for? Is because building occupancy relates to building energy use. And if we have a look at the energy demand or electricity demand in Ontario, and this is for 2 days, I believe in summer, you can see a Sunday is quite low, and then come Monday, once industry and the commercial sector gets fired up, we start getting these large peaks in demand of electricity. And utilities are very, very good at predicting what is going to happen to their network. And they do this so they can know what generators to start up, whether they need to start purchasing power from a neighbouring province or state, because if they get a larger than expected peak in demand, for example here on Monday, meeting that demand can be quite expensive, and that will have effects on grid stability, and it goes into the smart grid applications. So this blue line is actually the prediction by the utility grid, and the green line is the actual demand over that period of time. Once we get to a building level, and sorry about the quality of this graph, this is the power demand within the building that we had this test study in, and it was a mixture of offices and laboratories. So we had quite a large demand or background demand at night time to keep experiments running, and then as people arrived, it increased as well during the day. And there are numerous packages available out there, or methods out there, to predict how much energy your building is going to be using over the course of the day. And these models use weather forecasts and the current weather, and it also looks at previous history of the building, and if the building operator potentially knows how the building will operate given certain conditions. And there's a few methods, things like artificial neural networks or time series statistical models to predict the energy use within the building. And as Ian was saying with the simulations, the predictions and modelling are good to help with energy efficiency. We can learn how our building is operating, whether we can fine tune it at all, and also to help reduce peak demand. So if the utility knows there's an event coming on where they're going to be short power, they may be able to contact your building and go, can you reduce your load over this time period? You can look at what your building can do, so either reduce lighting demands or change ventilation and cooling over that period. So this, as I mentioned, this was part of a bigger project. So the Institute of Information and Technology, so IIT, were collaborating with Natural Resources Canada in a place called Varennes in Quebec on a real-time prediction model. So they had their building, and the IIT was involved in developing a model that looked at historical data for over a couple of years, looked at climate data, and also building system state. And we, in the indoor environment, said, well, would these models be enhanced by occupancy, a data stream of occupancy? And we had this proof of concept study over the summer months in 2008, 2009, I forget which year, looking at cheap off-the-shelf wireless sensors. And they used a backbone called N-Ocean technology, which was supplied by a company in BC called Ecoflex. So over the course of 3.5 months in our building, we recorded 4 different data streams. We recorded network logins, so as people turned up and started work for the day, they had to log into the network for internet, emails, shared drives. And we considered this to be one of our most reliable sources, measures of building occupancy. Of course, it had its known errors. For example, people could log off remotely, so if they were away at a conference, they could log on to access their data. And people would also log on at the start of the week and not log off or shut down their computer until the end of the week. And talking of log-offs, these weren't recorded in the data stream, so we had no idea when people were leaving the building for the end of the day or over lunch. We also measured network activity, where we just measured the amount of data, pure data coming in and out of the building. Of course, our wireless sensor network, which I'll discuss in more detail, and building electricity use over the same time period. So our wireless sensor network was relatively small. We had about a dozen or so sensors within the whole building, but we placed these in places that we thought would give us a measure of building occupancy. So we had a carbon dioxide sensor that we put a transmitter on, which would relay our signal back to our base station. We had these magnetic contact closure sensors that would transmit a signal every time the door was open or closed. And we put these on the external doors of the building, a couple of main internal doors, and we also thought a refrigerator door in a break room would probably give us a good idea of how many people were in the building over the course of the day. Motion sensors on 3 levels in the main corridors, and we also measured temperature and external illuminance over the course of the period. So the next sort of 3 graphs is the floor plan of our building. I don't really want to go into too much detail, but just to show you some of the issues that we have with wireless sensors and getting them up and running within a building, because each building is unique. There's no one-size-fits-all solution. And because our building was unique, we had a lot of lab spaces, large metal boxes for ventilation research. And without knowing those were in there, it took a while to get the system working. So, for example, this bottom sensor here on an external south door, it transmitted a signal that reached this green triangle here, repeat A, which would relay our signal back up to our base station on level 3. If we go over to our north door, we were unable to consistently get a set of readings from this north door because we had a stairwell, an elevator shaft, a research lab here, and we just weren't able to get through the 2 floors like we did on this other side of the building. As we move up through the levels, again, another motion sensor in the corridor. We also had 2 contact closures on our front internal door, so this was the main entry, a double door with vestibules. And again, there was a difference in the reliability between the external door and the internal door. So 3 or 4 feet made all the difference, and basically a glass panel made all the difference between getting signals reliably between these 2 doors. And then finally on level 3, this big star was our base station, so all the signals were received here. Carbon dioxide sensor, again our sensor in the refrigerator, and as I was saying before, it was a laboratory, so we had these big stainless steel chambers for air research, and these caused big shadows in the transmission of the signals. So anything on this side of the signal not transmit through that box, which is a problem with most EM waves in this frequency. So a couple of quick lessons learned. You really need to know the fabric of the building and how it operates to place your sensors smartly, and because there can be dead zones, construction throughout the building can play a little bit of interference. If you change building around, they might put up an extra wall, which will affect your signal quality. So over the course of 3.5 months, we collected nearly 700,000 telegrams, and it was estimated from a few calculations that approximately 15% of these went missing. Where they went to, I do not know. But as part of the data cleansing, we could work out they generally occurred over periods of times, whether it was a construction was happening in the building or the sensor was going flat because they had a little solar cell, so they were self-energy harvesting. They may not have been sending the signal at the same strength. So we removed these days from the analysis, and then we started to ask the question of, can we see basic trends within the data? So daily trends, weekly variations, and any special events. So a car park was closed over the course of a couple of days. Could we detect this in our sensor network? So we looked at the data several different ways. The first way we looked at it, and this is the activation count, so how many times a person or a group of people walked underneath this motion sensor, and over the course of the day. And we can see that weekends, public holidays are a lot lower, or zero, close to zero, compared to the working days of the week. Another way to look at the data is over the course of the day, and for every hour we accumulate the number of times the door was opening in this case. So we can see after midnight up until 6, 7 a.m. there's very little activity. Then over the course of the day we have pretty constant use over the course of the day until 5, 6 o'clock when the use starts dropping off. Again, weekends in blue and public holidays in green are different to the days in red, which were our working days. If we focus in on one particular day, we can sort of start seeing basic trends as well. So at the start of the day, we usually start work about 8:15, 8:30. There's a little bit of a, there's my mouse gone, a little bit of an increase in activity. There's a morning break around 10, so we get a bit more activity. I guess everyone buckles down and does some work before lunch, so they hide in their office. Come out at lunchtime. This door was right next to our break room as well, so you had to go through it to get to the coffee machine, and then afternoon break, and then go home time in the afternoon. So we're starting to get some confidence in that these simple sensors were giving us information that we could potentially use in an energy predicting model. And finally, large events in the building, could we detect them? So as I mentioned before, a car park was closed. So the door closest to that saw reduced activity over this period of time. On the first day, we're assuming that everyone used a different car park, so the increase in activity can be seen here, and they had a couple of different car parks to choose from. So we're assuming on the next day they were using a different car park, which they came through a different door, and because we weren't getting data from that door, it's hard to tell whether that had an increase as well, but it's sort of looking promising. There was a barbecue that we had for the Institute, and we can see where the door was held open for a couple of hours. A large meeting on level 3, and this was a door that they had to go through to get to that meeting. So we saw these effects in the buildings for large events. And finally, one that we thought may be there was a Friday effect. Fridays are an often flex day, so people can take it off because they work extra hours during the week. People take it off so they can have a long weekend. And if we have a look at the network logins and focus on the dark horizontal bar in the middle of the boxes, we can see that the mean network logins on a Friday is about 5 or so less than the rest of the week. So with that in mind, we then took that data, and especially the network logins, and a colleague of mine, Guy Newsham, did a set of time series statistical models to look at whether including this data improved the energy model, energy predicting model for our building by including the measure of occupancy. And the next two graphs I'm going to show you is an example of the results. So we'll start off with the red line is the actual building energy use. So to generate models, we looked at the first 16 weeks of data, generated the model. So this is the first Monday of week 17. The light grey line is the average or mean energy use for the previous 16 weeks. The dark grey line is the energy use the Monday before, and these are often general ways to compare data or predict the energy use on your day. And you can see that the light grey is very terrible in the morning and in the evening, but not too bad in the middle of the day. The Monday before is a bit better in the morning, but the same as the average in the evening, and not so good in the middle of the day. Our model is predicted by this blue line. So we used data up until 7 a.m, and at 7 a.m. we predicted the energy use for the rest of the day. And you can see it's not too bad for the first couple of hours, and then gets worse as the day progresses. What's a more likely scenario though is at 7 o'clock we predict for 8 a.m. We get a new set of data, retune our model, predict for 9, 10, and we keep updating until 1 p.m, I should say. And at this time, you generally have a good idea of what's required for the rest of the afternoon. And you can see that the the blue line follows the red line quite nicely. So by 1 p.m, should you have to reduce the demand, electricity demand in your building, you have a rough idea what it's going to be using, and you can start making decisions on how you're going to reduce your energy demand, whether it's dimming lighting, pre-cooling your building for the event at 3 o'clock, and things like that. But what sort of other information can we get from these sort of sensors? We looked at the time difference between the internal and external doors of our main entry and how long they took to close. We put this down to a variation in building pressure. So one door had a higher pressure against it, so it closed a little bit quicker. But what other applications are possible with just this, with this sort of data that may be useful for either modelling or just general knowledge? So that was the occupancy sensing part of it. There was another little part of this project which gets summed up in one slide basically, is what about knowing where people are? So if I walk into a building, the building recognises that I've walked into the building, and then it can start acting in the way that I like it. So the concept of hoteling in commercial buildings is becoming popular. If I walk into my cubicle and I have a smart badge around my neck, one day I might be put in a cubicle, and I can change my lighting conditions or my airflow to suit my preferences in this space. So it'll improve my comfort and potentially my health and well-being as well. The next day or the next week I come into work, I might be placed in a different cubicle. Instead of having to go through and adjusting all my settings again on a user interface, as soon as I walk in, it goes, hey, it's Benjamin. I know he likes his lighting dark, his airflow nice and high. Boom, my settings are there. And you could start tying this into other things. You could have a digital picture frame on the cubicle wall. It imports your photos, changes across your speed dial settings on your telephone, things like that. And it's expected or predicted by including all these different functions, so personal selection in lighting levels and airflow, as well as turning lights off instantly when you leave. You could probably save potentially about 30% over a standard system. How are we going for time? Pretty good. So to wrap up this little final part, we found that by including occupancy sensing data, we can improve energy use prediction models. The improvement wasn't great, but we put this down to the fact that our building was unique and quite different from a standard commercial building. This occupancy measure can come from either existing data, so IT data, and there may be other potential sources out there that we haven't really thought of yet, or we can obtain it with new off-the-shelf sensors by measuring, the number of the times the door is used, or number of times a group of people walk down corridors, things like that. So that was looking at potential peak demand responses in commercial buildings. And I'll take probably 5-10 minutes to finish off with some work we're doing on some residential smart meter data. And the reason why I'm showing you this is we got this data from Ontario Power Company, but Kevin was able to put us in contact with Idaho Power, who gracefully gave us the data to do some analysis with as well. So the smart meter data set that we have worked on and plan to do the same analysis with this as the Idaho data had approximately 13 houses in total. Some of these had hourly data for 3 years, but the bulk of them for only 1 year. And we also had survey data for 360 houses. This data just gave us things like air conditioning use, air conditioning, heater types, and a few other characteristics of the house. And this analysis in particular looked at the savings occurred by a peak saver program in Ontario. And in this program there's 195 houses, and The rest of the houses we put into a control group for comparison. If we look at the mean energy use of a house, and again, the graph quality is not that great, but we get a good idea. In the winter months, so at the start of the year and at the end of the year, our energy load is a lot greater. It's darker for longer periods of the day, so we're using more lighting, and we've got to push heated air around the house to keep it nice and warm. Our changeover seasons, spring and autumn, fall, since I'm in North America, has a reduced energy load or base load, because the conditions outside are closer to what we prefer. Once we hit summer though, we start getting these large peaks in energy demand for houses. And this is because we want our house chilled to a nice 25 degrees, 20 degrees when it's 30 degrees outside. So we're using our air conditioners a lot more for short periods of time. And as I mentioned before, it's really hard for utilities to meet this demand. If they can't, you end up with blackouts or brownouts across the network. If we focus in on how much energy a house uses over the course of the day, and we'll start by looking at the left-hand chart and this solid green line. This is the mean energy use in summer. This shaded area in the graph is the peak demand of the utility, and the peak demand of the house falls out of this zone. But there is some room for the mean energy use to decrease of a house. Weekends, the dotted line, again, is different from a weekday. You can start seeing that people wake up an hour later, so the energy doesn't start being used until a bit later in the day. People are at home doing the laundry, so their daily energy use is a lot greater. When it comes to winter, our peak demands start matching up with the peak demands of the utility, and again we see similar trends on the weekends with people waking up an hour later and a larger energy use throughout the course of the day doing laundry and other activities. So to reduce the peak demand in the residential sector, there's several different trials out there. The first of these is peak pricing, so charging consumers a peak price at peak times, and this will encourage them to use less energy at this point in time. Time of use rates try to flatten out the demand over the course of the day and aren't really aimed at peak periods. The Peak Saver program in Ontario uses a direct load control method where a volunteer signs up to the utility to be a part of this program. They come in, they install a device on your air conditioning unit which cycles the chilling plant on and off. So over the course of 4 hours, your house may raise by a couple of degrees. And they promise a maximum of 10 events per year, with each event lasting 4 hours. So the day before, utility will go, we're having a peak event tomorrow. You have the option of opting in and out of that event. So if you're going to be home, you're sick and you need the air conditioning, you can ignore the signal and keep your house up running as normal. The question is how much energy is saved by these programs? And to calculate that, we've got a quick chart up here. This red line is the mean energy use over the summer. The blue dotted line is the temperature profile for this day. And if we look at the purple line first, this is our control group. And this is the ones those that aren't enrolled in the Peak Saver program. The green dashed line is the actual energy use of those enrolled in the Peak Saver program. To get a better estimate of the savings, we've got to try and normalise these two values. So by choosing a couple of hours before the event, we can reduce the Peak Saver program down to what the control group is, and we can see it matches up just before the event and again after the event. So these values at 1, 2, 3, 4 is our estimate of how much energy is saved during a peak event on the network. There's 5 events over the summer of 2008. The graphs are all very similar. This one in the middle is quite interesting because you can see the temperature actually drops by a few degrees just before the event. So a storm actually moved through the area, reducing the temperature, and you can also see the effect on both of the control group and the peak saver group. Their energy also decreased in this time period due to this storm in the area. So some preliminary energy savings. Each event saved different amounts of energy, but on average, they saved somewhere between 10 and 20% over the course of the 4 hours. As time progressed in the event, you can see that the amount of energy savings decrease as well. So what's next with this data? We're going to plan to do a complex time series analysis, similar to what we did with the wireless sensor network data, and compare the results gained from that with these results from this basic analysis. And of course, repeat the data analysis on the Idaho data. And this will hopefully go to improve models and allow for greater generalizations at the end of it. That is all for me. I guess if you've got any questions, Ian will come to the front. You can ask him questions and I will...
You'll answer them.
I'll answer them.
I had a question for Ian. How much was air pollution considered on the Lighthouse Building in Glasgow? Because when we were at the UK City of Arts and Architecture event, we were shown buildings by Alexander Greig Thompson on which the crustation was partially removed, but then only to discover that it was actually protecting the brick. And so they stopped doing it because they're such wonderful buildings. I wondered if that is an effect on the modern materials that you were using in that.
I can't directly answer that question. On the, I know it's a huge issue though, because growing up in Scotland, the air pollution and smog from burning coal and fires in people's houses was a huge issue. And in London in the 1950s, I think, it was like quite often there was really bad smog events. And people talk about the LA smog, there's also London smog, are the two typical smog events. And that caused a lot of this blackening of the brick and the stone and all this. And the buildings, as I was growing up, you'd see scaffolding going up and they'd start to work and then they'd stop and the scaffolding would come down and then it'd go back up again, down and up and down and up. As they were trying different technologies to clean the stones. I know nothing about the details of that and the impact that has. The air quality is much, much better now. You're not allowed to burn coal that will give off smoke or anything in an urban area in the UK now, or most UK cities. So the principal source of air pollution is cars and traffic.
I was just thinking that in a modern office environment, it seems to me the best sensor you probably have is the IT network. And if you're monitoring traffic on that, you have an extremely good picture of activity. And you could even tap into things potentially, I don't know the details, but like the Microsoft Exchange server that manages the Outlook email system, you could get the calendaring and meeting reservations and all that stuff. You can see when people are having meetings, when they're at their desk. You can just really dial into what's going on in an office.
We did try to get that extra data, so we also had swipe badges to get in and out of the building at a certain periods. We weren't able to get that off the facilities of the campus we're on. Emails we tried to get as well, like just some data we weren't able to get access to, unfortunately. The network logins did prove to be to be the better measure of building occupancy. What would have made them really good was if we had a time when they logged off. But if you don't ask the right questions, you don't get the information you require.
I was thinking you could really fine-tune the setup of the power states of people's equipment and stuff, and printers and stuff,
Yeah.
by looking at network activity and stuff.
Yeah, you could definitely tie all that in as well.
How close are these, where your smart badge and you walk into your cubicle and it puts your pictures on the monitor and your own speed on them, or is that happening anywhere?
So the picture I showed you of the guy with the badge, that's our demonstration badge. So that's the size of, I guess, a packet of cigarettes. Ideally, I don't have my NRC badge on it, but
I feel like a credit card.
like a credit card would be the size that they'd be able to get them down to. And I think you can get RFID badges about that size anyway.
My question isn't really about the badge, it's
Yeah.
about, does this happen, this
Not
smart
yet.
cubicle?
This is a proof of concept for us, and we're just starting to get that up and running. In the photo that I showed you as well was our indoor environmental research facility. Is that correct? IERF.
Oh, no, facility, yeah.
Yes. Sorry, we have all these acronyms and I forget what they stand for. And it's a thing of 6 cubicles. So we're in the process of showing that as a demonstration and getting that up and running now. Like, there's a lot of fine tuning and talking between different protocols as well. So our system is very, very basic, but hopefully one of the end results of this whole ICT project is to push it into the commercial realm. So hopefully only a few years off.
And do you have a model that shows, I imagine there's some expense in installing this system.
Yeah.
But it would be balanced by energy savings, by the adjustability.
I'm sure they are. I'm not involved in that end. I can tell you that our system is probably not very energy efficient. No, definitely not. But you'd assume a professional one will be a lot better than what we are currently using. We use a lot of resources to get the information out that we want, which in a professional system or a fully operational system we wouldn't use. So we use something like probably like 4 or 5 computers to get that information at this point in time, and you'd crunch that down into one.
Yeah, we've also got a bunch of monitor data from real buildings and from our lab studies where we've given people control, say, over their lighting with increased lighting capacity installed, and some people select brighter lighting than would be the standard installation, and some people like it darker. On average, that's a reduction in lighting load when you give people a choice.
So that would be my next question. If you give them more adjustability, does that mean they would use more light and more heat or more cool?
Yeah. So
Some do, some don't on average.
yeah.
Average is actually less.
Yes. Yeah. I forget the exact number off the top of my head, but I think it's about 15%.
Sounds about right.
I think it's about a 15% reduction in average desktop illuminance chosen by, I think, 425. So I think the standard is 500 recommended practices, and they on average choose about 425 lux. So it's a decrease. You get your typical bell-shaped curve, but it's lower than recommended practices.
Yeah, I actually presented some of those findings last time I was here, so it's archived if you
Yes,
want more.
yeah, I forgot about that actually. It's the presentation is probably here that Guy gave this time last year or something.
Have you used occupancy sensors on the, on the lighting or the computers in individual workstations, and how did the people react to that?
So that's in the same presentation that Guy gave. So a couple of the systems we looked at had personal control. So let me go back to how do we zoom this up. So the couple of systems that we looked at had a personal control like that, and we had indirect luminaires like this that also had an occupancy sensor. And by doing a few different calculations, we could work out how much energy the occupancy sensor saved. And I think typically it's around 30%. Don't quote me on that one, but it's definitely in Guy's presentation. It is remarkable if you're able to turn the lights off straight away when people leave, etc. It does adjust it. So I think the profile of the luminaire is on and off, so you do save a substantial amount with occupancy sensors, photo sensors, and dimmable lights. But there's the presentation that Kevin's talking about has that information in it, definitely.
And the other thing, we're very multidisciplinary in our group, and we have 2 psychologists on staff. So a lot of our studies, we've not only looked at the energy savings and the lighting levels and things like this, but also the human satisfaction and job satisfaction and organisational productivity issues. So we try and collect that data as well. And I'm sure Guy would have covered that in his presentation.
So related to that, do you do studies on, say, the ability to look out a window or to see green out a window causes, better comfort or productivity or anything like that?
Our questionnaire, we definitely ask if people are next to a window. I don't think we've got any questionnaires that say, what are you looking at? So, we ask where people are in the building and if they have control over any of the aspects. One of the main ones with windows, proximity to the windows, if you've got a blind to control the lighting there.
So do you have conclusions that show that having a window nearby and the ability to adjust the blind increases satisfaction or comfort?
Pass. You'd have to ask the psychologist. It'll be all of our publications are on our website. That's one of the really useful. Do you have the slide? We keep copyright of everything we do, so that no matter what, all of our publications are available on the website. So once you go in there and fight your way through the navigation, you can get to it. But if you put in, say, Guy Newsham or Jennifer Veach, Jennifer's our senior psychologist.
Yes.
I have a question. Your presentation earlier today, you talked about that natural daylighting is the right in Scotland. Is that just in the downtown area, or is that just all of Scotland? And is there building have to be a certain height for you to, because you also mentioned that people can challenge or protest a building that's going up that's going to impede their natural daylight.
Now you're testing my memory. There's a right to light. Whether that's just in Scotland or the whole UK, I'm not sure. And I'm not sure there's any hard and fast definition of what that right is, which was where a lot of these studies with daylight factors and solar and the direct shading became kind of very subjective, whether it was an effect or not. It's like the planning department has the final say on whether something gets permission to be built or not, and all sorts of things are taken into consideration before that permission is given. If that goes any way to answering the question.
We have a good resource here there, and I think it is all of the UK. We've got a book on light surveying in England, believe it or not. And it's been an interesting the law dates back to like the 1100s. And if I understand it correctly, if a window has enjoyed a view and access to daylight for a period of 25 years or more, you have to maintain that access to daylight and that view, or you can go after them in court. And so then the fine line is, well, how much daylight? And
Yeah.
this is the whole daylight factor conversation. And right now, I think it's a moving target, and it sort of works itself out in courts and precedents, and probably just gets updated. But one daylight factor is the number I remember.
Yeah.
But I don't know how often those things are getting poked at.
The other interesting thing in Scotland in the 1800s, I think it was, your property tax was based on the number of windows you had. So you see a lot of properties that actually just have bricked up windows, and they've been like that for 150 years.
Any other questions? Just like to thank Ian and Benjamin for coming all this way. And again, thanks to our sponsors, Idaho Power, Northwestern Energy, and Better Bricks. And then a reminder, if you haven't signed in yet, please do so. We also have some evaluation forms. If you can take a couple seconds to fill those out, that'd be great too. Thanks for coming.